University, and he's going to tell us about 3 lessons learned from implementing PLO framework for data exploration.
Exactly. So, hi, my name is Amit from Aviv University, and I wanted to share with you several lessons that we learned from implementing the DRL framework in the context of data exploration. We do believe that the lessons we learned are not only relevant for people that are interested in data exploration, but maybe you can use some of the lessons that we learned into the context of your own problems. So data exploration is this interactive process where a user explores the dataset by performing a session, namely a sequence of analysis operations, like filter, group by, visualizations, etc. And after executing each action, the user examines the results and decides which and which action to perform next. It's a very important process that is performed in any data-driven task, where the goals are to understand the nature of the dataset, discover some interesting aspects of it, and even estimate its quality. The problem is that it's a very difficult task. So not only for big data standard reasons, such as data size, etc., but it also requires profound analytical skills and some familiarity with the data domain. So this is not a task for everyone. So after we've been doing several research projects in the context of EDA recommender systems, we thought maybe we should take the next step and cut the user off the loop and use a deep reinforcement learning in order to generate exploratory sessions from scratch. So why even bother? Because DRL is working surprisingly well for very difficult tasks such as playing Go and Atari games, and even show some promising results in several driving cars. And the main advantage, at least for us, is that it learns only by self-interactions and requires absolutely no label data. So this sounds appealing, and we almost ignored several of the red flags. Mainly that it currently works mostly on game-like environments, so there are not so many production systems that use deep reinforcement learning yet. And sometimes, even when it does work, it may just overfit to some weird patterns in the data, like this poor cheetah here that was supposed to learn how to run, and instead it flips on its back, and it tries to awkwardly move in the space. So 2 seconds about reinforcement learning. Very briefly, it's about an agent interacting with the environment, like in the first keynote that we saw today. So the environment should provide the agent with an observation about its state within the game. Using this observation, the agent should choose which action to perform. In the game environment, it could be moving to the left, moving to the right, or making a jump. After the agent performs an operation, it's supposed to get a reward. It could be negative or positive, or a positive feedback about his action. And the goal of the agent is interact with the system as much as needed in order to learn a policy that maximizes the mean reward. So now we want to take this and project it in the context of data exploration. So we are actually talking about the same thing. So it's mainly an agent that's supposed to interact with a data set, but through this environment. The environment should provide it with some sort of an encoding of the data sets and result sets so it could see it. And the agent in turn should choose an EDA operation and also receive a reward mentioning how good was this action. And hopefully, by interacting with the dataset or a collection of datasets as much as needed, the agent will learn how to maximize the reward, and also hopefully we can use this agent to generate meaningful exploratory sessions. So that's where the fun part of creating a visionary system ends, and the troubles of implementing a visionary system begin. So during about a year or so, we did implement a prototype system that performs EDA from scratch using deep reinforcement learning, and we learned 3 valuable lessons. The first lesson is about how to design an environment for EDA from scratch, and the questions here are how to allow the agent to formulate EDA actions. And the second question is what information to include in the observation vectors. These are very important aspects in order for the agent to interact with the dataset. The second lesson was how to develop a reward system, namely how to evaluate if the EDA actions are good or not in order to provide feedback for the agent. So that was also a very difficult task that we somehow managed to overcome. And the last and most frustrating lesson that we learned is that we basically expected that after we formulate a DRL problem for EDA, then we can actually use off-the-shelf DRL algorithm that can do the work for us. It was very frustrating to discover that it's not the case, and we actually have to dive into the internals of the neural network architectures and create an architecture of our own. So for the sake of time, we will only cover the first two lessons, and you're welcome to reach out offline, and I can tell you all about the architecture design. So lesson number one, how to design the EDA environment. And question number one is how to formulate EDA actions. So intuitively, like humans do, we wanted to allow the agent to perform SQL queries. But the problem is that SQL queries are very difficult for machines to formulate from scratch. And as doing EDA is difficult as it is, we wanted to make it easier on the agent's life and allow it to compose actions more comfortably. So we did go for a parameterized action space where the agent should choose first the operation type, like filter or group, and then it has to instantiate the parameters values. More importantly, we use a set of atomic operations. So it's, if you can see, it's filter with one condition, employ a group by on one attribute with a single aggregation function, in order for the agent to build the complex result set gradually. So these are the advantages of this kind of formulation of EDA actions. And the advantages are that, first of all, it's much easier to compose, for a machine at least, than using a free-form SQL. And the second advantage is that it allows for us to better control what the agent does, because it only makes atomic operation that we can give it feedback, namely the reward, after each such atomic operation, and it gives us better control. So this is the interface that we made for the agent. And the second task was to think what kind of information to include in the observation. So how to represent the agent, how to represent the state of the EDA game to the agent. So basically we have to take the result display that can contain grouping and aggregation, etc., and construct some sort of a numeric feature vectors. So we didn't go over the top here and just manually extracted statistical features, like the number of distinct values, some statistics about the grouping, such as the group sizes and variance, etc. And we ended up with a vector that somehow concentrates the information about the current result set. And then the second question was, is that enough? Is that enough information for the agent to make good decisions? So we moved on and implemented the rest of the components of the system in order to test it in practice. So at the bottom of the slide, you can see the learning plots. The x-axis is the number of training steps, and the y-axis is the average reward. And the orange line here that you see is the learning plot of the architecture when we only encode the last result display. So what you can see is that it does converges, luckily, but it only converges after about 3 million steps, and I don't know if you can see it from the back, but it do display some fluctuation, so it's rather unstable, even when it reaches convergence. So we were suspecting that this is not a sufficient representation, and the agent might be missing some more information about the session that it just performed. So we tried to add information to the observation, and the second solution that we thought of is simply adding the action number to the observation vector. So if it's the first action, then we just add an element with the number 1 to the observation vector. If it's the second action, that we add the number 2, etc. So as you can see now, the blue line symbolizes the system architecture when we use the second solution with the action number. So now you can see that it converges much faster with a higher reward. So we were very happy at first until we examined what the sessions that the action generates. And we were not happy because no matter which data set we asked it to explore, it always made the exact same actions. Namely, it just overfitted the action selection process into the action number, which is obviously not a desired behavior. So finally, we decided to give it more context and just concatenate to the observation of the last result set also the observations for the previous two displays. So it can get some more context information about the session that it makes. And this time, as you can see with the green line, it converges to an even higher reward, and now the overfitting phenomena was eliminated. So to summarize the insights of this lesson is, first of all, when we control the action space and limit it to simple atomic operations, it allows us for better control, and it's much easier to debug learning process. And the second insight that we have is the kind of information that is encoded in the observation vector is very critical for the agent to make good decisions, and for us to obtain a stable and a converging learning curve. So that's about the environment design. The second part was designing a reward signal, where the task was how to define and implement an explicit means for evaluating exploratory actions. It's not existing as far as we know. So we will not go into much details here, but we wanted the actions that the agent generates to be, first of all, interesting. So it should produce interesting results display. Second of all, it should create diverse result sets in order to capture several aspects of the data, not just one. And third, and most importantly, the actions that the agent makes should be coherent and understandable to human, because some user should be at the end of this process to watch the actions that the agent performs, to watch the exploratory sessions, and hopefully to gain insights quicker for the data set. So someone needs to look at the agent's action and understand what they do. So long story short, we managed to implement each of these components, and after several months, we were very happy to see that it converges. Namely, that each of the reward components that we just described, the interestingness, the diversity, and the coherency, were converging, and the weighted sum, which is the final reward signal, is the blue line, was also converging. We were very, very happy, until again, we examined what the agent does. Then we were less happy because we saw that the agent still doesn't behave right and demonstrates some weird behavior. For example, it performs much more group by operations than filter operations, which is obviously not a desired behavior. And second of all, the first few actions in the session were pretty good, but as the session progresses, we saw that the agent performs worse, and the action make less sense. So we examined the reward signal, and we discovered that there is a correlation between the reward that we give the agent and the undesired behavior. So for example, in the right-hand figure, you can see that the reward is decreasing as the session progresses. So for the first few steps, the agent gets high reward on average, and then as the session progresses, it gets lower and lower reward, which obviously motivates the agent to perform well on the first few actions and then to slack off on the rest of the sessions. The same correlation was about why doesn't the action perform filter operations, because as you can see in the left-hand figure, the reward that it gets for filter operation is lower than for the group by. So obviously the agent is more motivated to perform group by operations than performing filters. So we had to track down each unwanted behavior of the agent and then find out the reward components that is responsible for this unwanted behavior and fix it and tune it. And only then we were able to reach convergence and get the desired behavior that we want. So the summary of the insight here is once you reach convergence, it's not enough, and you also need to analyze the agent's behavior and adjust and tune the reward accordingly until you get the behavior that you want. That's only in the case when you don't have a clear explicit reward signal, which was the case in EDA. So the third lesson was whether we can use off-the-shelf BRL algorithms And unfortunately, we found out that we can't because the action space is very large, yet mostly discrete, which is not the natural situation for DRL algorithms. So you can find all the details in the paper, or reach out after the talk. So we had to go to deep dive and form an architecture of our own that can deal with the parameterized large and discrete action space. It was very cool. So the final message for my talk is that DRL is indeed very cool technology and may be promising, but this is not a black magic, and it's not suitable for all the problems in the world. And you have to think carefully whether your problem suits the DRL. And also, DRL doesn't come to you, it's you go to the DRL, because you need to carefully formulate the problem such in a way that the DRL can work correctly, which mainly it means that you have to design properly the environment and the reward signal. So if you want to see a working demo of the prototype system that generates EDA session from scratch, you're more than welcome to see our demonstration in the upcoming CIKM conference in Beijing this November. And that's it. You can take questions.
Questions, anyone? Yes, can you please use the microphone?
Hi, yes, thank you so much for the excellent presentation. So I guess I have a question. So do you think at this point, is it practical to use deeper reinforcement learning for interactive data explorations? Because these type of tests usually are somewhere data dependent. So for instance, the interesting measure might be different. So the interesting measure that you use to design your reward might be different, depends on data and depends on the exploration test that the user performed. So considering that it takes a long time to actually learn a good reinforcement learning model, do you think right now it's practical to actually use it interactive data exploration?
Thank you. That's a very good question, because whether we can actually do it in practice for the general setting where users can analyze data sets from all types with different purposes is a very big challenge. Although our goal here was to just make a proof of concept. So we only took data instances of the same schema. So we basically have the fixed schema. But each component that you mentioned is a very good future research. So evaluating the interestingness of data analysis action is a must-have future work. Also including personalized preferences is also something that you should consider, because people often analyze data sets for different reasons, and what's interesting for me is not necessarily interesting for you. So all these components should be taken into account and expanded and incorporated in the system. But our goal here in this work was only to make the proof of concept and see whether even in a limited settings with a limited number of data sets and operations, we can make sessions that make sense.
Thank you so much.